Alrighty, folks, hello and welcome back. This is module number 2. So we've completed everything for module number 1, which was the design and analysis of experiments. Here, what we're talking about in module 2 is a continuation of what you would have done in your first stats course, or if you're coming from Stat 2601, this is talking about modeling. So how do we add variables to our model? And what we're going to be looking at in this lesson is which variables to add. And if sometimes maybe those variables do not fit the assumptions, such as linearity, how can we adjust those variables such that we now meet that criteria? So what we're going to be looking at today is looking at using dummy variables to model qualitative independent variables. So when we have categorical data in there, how do we include those variables? It's not just as easy as throwing them in there. So again, in the 2601, all we've done is add numerical. So now we're dealing with categorical. So it's kind of a slight change of what we did, or a slight continuation of what we did in the first module, dealing with categorical variables, adding them in the different levels, testing to see which one was the better outcome overall. So we're going to be doing that, and we're also going to be looking at squared and interaction variables. All right, so let's jump into this. All right, so using dummy variables to model qualitative or categorical independent variables. While the levels or values of quantitative independent variables are numerical, the levels of qualitative independent variables are defined by describing them. So again, in the numerical data that we have, we can do basic arithmetic. Those sort of things make sense. When we're dealing with a categorical variable, this is not true. If we have two cities, suppose we have Ottawa and Montreal, we add them together, we're not going to get Toronto. That doesn't make sense. So basic arithmetic does not work in this case. There might be the ability to order the different levels. That's perfectly fine. But in terms of actually being able to do basic arithmetic, that's out. All right, so far we have only looked at including quantitative data in a regression model. However, we may wish to include descriptive qualitative data as well. So just as an example here, again, kind of going back to the city thing that I was talking about just a second ago, suppose we wanted to include the city of respondents. So again, if we have two cities, we can't simply add them together. But how do we treat this variable? Do we just kind of throw it in as we normally would? So if I have a numerical variable, this could be just x1 in our model, and x1 can take on any different sort of value within its given range. Does this work the same for categorical? Well, the answer is no. So this is why we're going to have to look at including what is called a dummy variable. So we can model the effects of different levels of qualitative variables, and I pause all the time for that one because I keep getting mixed up with the quantitative, qualitative, or categorical, numerical. But again, we're dealing with categorical at this point in time. So the different levels of qualitative variables by using what we call dummy variables or indicator variables, depending on what textbook you are referencing to, or if you're going online, depends on how they say it, but it means the same thing. All right, so such variables are defined so that they take on only two values. So it's either 0 or 1. Doesn't matter how many levels that we're going to be dealing with. We'll talk about what happens when we have more levels. But these variables, that when we include them into our model, we can consider them either on or off. 0 or 1, true and false, that is it. So we're going to start off with kind of easier examples. We're going to start off when we only have 2 levels, then we'll move up to 3 levels, and then we can generalize it from there. So starting off the easy case, only 2 different levels. So we have a categorical variable, 2 possible options. That's it. That's all. So let's say in this case, we're building a model. I have 2 variables, x1 and x2. x1 is going to be some numerical variable. Again, it doesn't really matter what we're measuring at this point in time. It's just going to be some numerical variable. And x2 is going to be our categorical variable. And again, it can only take on 2 levels. So right now, we're just going to reference them as 0 and 1. So 0 represents the first level, 1 represents the second level. So using a dummy variable, we consider the following regression model or linear regression model. So we're trying to model our response, which is y, and this is going to be explained by our equals beta naught. Again, I'm talking about beta, so these are the population parameters. These are not our estimates. Again, we'll estimate based upon the data that we have, but right now we're talking about the model in general. So I have my beta naught, which is my intercept, my beta 1, which is my scalar for my x1 variable, x1 again being that numerical variable, and beta 2, x2. So again, so far it looks like exactly how we would have treated things beforehand. But how we treated things beforehand is we could really plug anything. Not necessarily anything, within the kind of given range. But again, it's a numerical variable, so we can plug whatever we want into there as long as it fits. But x2, again, this can only take 0 or 1. That's it, that's all. All right, so a kind of key thing to note here, again, when we're talking about a linear model, we're talking about linear in terms of the parameters, not the variables themselves. So typically with dummy variables, we use the variable d instead of x, just for clarity. So I could have written this model as y is equal to beta naught plus beta 1 x1 plus beta 2 d. And usually I'll do a subscript if there's different levels, and you'll see why in a second, because it's going to help us reference what level we're on. But again, we'll get to that when we start kind of expanding this to 3 levels and more. All right, so what happens, again, not when I'm focusing on my x1, but specifically focusing on my x2. Again, x2 can only take 0 or 1. So if my original model here, again, y is equal to beta naught plus beta 1 x1 plus beta 2 x2, or d, because I'm saying d is equal to x2, if I plug in the values for d, which are just 0 and 1, what does our model look like? So when d is equal to 0, well, this whole term, it doesn't matter what beta 2 is going to be, because beta 2 can be anything. I'm multiplying any real number by 0. That term just disappears. So all I'm left with in my model, and this actually should be a capital Y, not a lowercase y, y is equal to beta naught plus beta 1 x1. That should be familiar. That equation should be familiar, because that is the equation of our line. A line with beta naught being our intercept, beta 1 being our slope. So this could look something along the lines of, that's a horrible graph, but this is my y, this is my x. Just go with me here. Can I do different colors? That's the key. Ooh, I can. Excellent. Let's do green now. So let's suppose my intercept and my slope, I have a positive slope, I have a positive intercept, so it could look like a line that looks like this. This could be my y is equal to beta naught plus beta 1 x1, and this is, of course, when d is equal to 0. All right. Let's get fancy. Let's change up colors here. Let's go to blue. Why not? Blue's great color. Okay, so when d is equal to 1 now, what do we get in terms of our original model? So again, back up to that last term, d is equal to 1, doesn't matter what beta 2 is going to be, because I'm multiplying it by 1, which means it does not change. So this is always going to be beta naught, again, this should be capital Y, beta naught plus beta 1 x1 plus beta 2 times 1, or just beta 2. Now notice here, I can combine my like terms. I have 3 terms, 2 of which do not have an x. These are just constants. So that's my beta naught plus beta 2. I can group these together. So now my equation is y is equal to beta naught plus beta 2. Notice this is now my intercept. This is where I cross the y-axis. And I still have my beta 1 x1. Now notice that last term is exactly the same as my last term here. So my slope is not changing. That's kind of a key part. My slope is not changing. But what is changing is my intercept. So how is my intercept changing? My intercept is changing by this beta 2. Because my original intercept, when d is equal to 0, so when I was on that very first level, my intercept was beta naught. But now when I've changed from that first level to second level, how is my slope changed? My slope is changed by beta 2. So it's taken wherever I was beforehand for that first level and I've changed it by beta 2. Now, beta 2 could be positive, it could be negative, so I could be going up or down along my y-axis. If it's positive, I'm going up. If it's negative, I'm going down with respect to where I started and where I started. That sort of reference level, that 0 level, and it doesn't have to be the first level. We'll talk about that again when we get a little bit further, but we have to set a starting point. And let's just say in this case, that starting point is the first level. So the difference is now from the first level to the second level is just a change by beta 2. So how would this look? Well, if it's positive, if beta 2 is positive, well, I would have something that could look like this. Again, key part, slope is the same. So how they're both changing. As I go across to the right on my x-axis, they're both changing at the same rate. They have the same slope. So this is my y is equal to beta naught plus beta 1. I should write this as beta naught plus beta 2, there we go, plus beta 1, x1. So they're changing at the same rate, it's just their starting points are slightly different. So there is this gap. And if this is my starting point, so this is level 0, and this is my level 1, when we change up, again, how it changes in terms of as x increases, y is going to increase at the same rate. But those starting point, that initial starting point. So if we're talking about sales and level 0 versus level 1 in this example here, which you're seeing when I go to level 1, I start higher up, means if I'm on level 2, if I'm offering something on level 2, it could be a different city, it could be, we'll talk about in our next example where the stores are located. If I'm on that second level, in this case level 1, or if I'm talking about level 0 being the first, level 1 being the second, if I'm on level 1 in this case, my sales are starting higher than what I would be on the first. So if I were to graph my data, what I should be able to see is if I do kind of lines of best fit, I should be able to break apart my two different levels in this sort of way. How they change, the slope should be the same, but the intercept should be different. All right. So the dummy variable allows us to model situations where we have the same slope but different y-intercepts. So here beta 2 is the effect on the mean response. So again, on average, what are we expecting to see what happens with our y being the response variable compared to beta naught. So this is kind of the key part here. Anytime we reference n, this will be the same if I have 2 levels, if I have 3 levels, if I have 50 levels. We're always picking a reference point, and in this case, we're just treating that as the very first level that it could take. It doesn't necessarily need to be, but there has to be a reference level, and so it's compared to, in this case, to beta naught. That's starting point, so compared to beta naught, that's starting point for the very first reference point, or in this case, the very first level. So let's change my colors back to red, keeping things consistent here. All right, so next screen. Let's jump into our example. So suppose that Electronics World, and I know, great names for the stores. Electronics World, a chain of stores that sells audio and video equipment, has gathered the following data. So we have 10 observations or 10 different stores. Now we also have the number of households. This is going to be the number of households in a given region or around the stores in itself. So this is going to be a numerical variable. We'll just put an N up here for numerical. The next, what we're dealing with is the location of those stores. This is going to be categorical. So it's either going to be a street location or it's going to be a mall location. And last but not least, this is going to be, I'll put R for our response. We're trying to model sales. Or actually, I shouldn't write Y. I shouldn't write R, I should write Y. This is our response variable. Doesn't matter if we keep it as R or Y, same thing. But this is the response. This is what we're trying to model. We're trying to model sales, again, based upon the location of the store and the number of households. All right, so this is kind of just quickly summarizing what I just said. So the data concerns store sales volume in July of last year, Y measured in thousands of dollars. The number of households in the store's area, which is X measured in the thousands, and of course the location of the store. So again, location is the categorical, the numerical is the number of households, and the sales is the response. So what we want to do first, and there's three parts to this. The first thing that we want to do is plot the data and discuss why the data plots indicate that the model, and this is the model that we just kind of spoke about here, where I have y is equal to some beta naught plus beta 1 x1 plus beta 2 d slash m. So our dummy variable m, this is referencing the mall location. So again, we have street location, we have mall location. And there's going to be a reason why we're putting d slash m in this spot, and I'll talk about it again when we start looking at the model and why I'm picking certain things as the reference or the starting point of our categorical variable. So we want to discuss why this might be appropriate, or this model might be appropriate to describe the observed data. Part B of this, we want to interpret the practical meaning of beta 2. So what does it mean in terms of this example here? And then what we want to do is we want to test whether or not our assumptions. So first what we're going to do is we're going to graph this. We're going to see, does this make sense to include this in here? But then what we want to do, and same thing what we were doing beforehand, is do we want to be, or we want to be able to say, we're including this in here because it's statistically significant. Not just the fact that I've grabbed a couple stores and it looks like there's a difference, so I'm throwing this model in here. I want to actually be able to test at a given significance level whether or not it makes sense to include this in here. Was this just randomly happening that it looks like we can add this different variable in here? Or is it true that there is a statistical significance to add this in? So we're going to do an ANOVA table for this model. We are going to do a hypothesis test. Our hypothesis test is testing whether or not beta 2 is equal to 0, or the alternative, beta 2 is not equal to 0. So it's the null hypothesis is there really is no difference between the different levels. What we're seeing here has just randomly happened by the selection of stores that we have. Versus the alternative is this is not just random. This did not just happen because we selected these stores. There is statistical evidence showing that there is in fact a difference. And that difference is, we don't care if it's positive or negative. Again, this is how that intercept is going to change. We're just saying it's not equal to 0. So we're going to set alpha or significance level to 0.05 and again interpret the practical meaning of the results of this test. Whew, that was a lot of things to say. And we want to use a 95% confidence interval to interpret the interval for beta 2. So again, when we're building that model, what we're doing is we're estimating beta 2, and we want to be able to find a 95% confidence if we do in fact reject the null hypothesis. So if we're rejecting the fact saying that there is no difference between the levels, saying that there is a difference between the two levels, then we want to see, well, where is the true value? Where is beta 2 actually sitting? And we want to be 95% confident in that. So we have our estimate. So we want to take our estimate. We want to go to the left. We want to go to the right. We want to open up that space and say, okay, the true value is going to be somewhere in this range. And again, this only makes sense if we reject the null hypothesis. It does not make sense if we fail to reject. So if we fail to reject, we don't have enough evidence to say that there is a difference between the levels, and in that case, there's no point to running a hypothesis test. Sorry, a confidence interval. There we go. But if we reject the null hypothesis, we say that there is a difference. Now we want to build that confidence interval to say, okay, well, where does that true value lie? Not what we got based upon, so not our estimate based upon the limited data that we have, but where is the true population parameter in this? All right, so this is what we want to do. Now let's jump over to R and do the work inside of there. All right, so I have not installed all of these packages because I wanted it to be pretty much the same as what you folks have. So I'm going to be installing as we go. So if there's any errors along the way, it's going to be the same errors that you're getting, and we should be able to correct this as we go. So notice, I know that there's packages not installed because when I first opened the R script file, so this is lesson 3.r, I have this yellow bar and it's telling me things are not installed. But what's not installed? So the package readxl is required but not installed. So I can click to install it here, or I can say don't show this again. I'm always going to leave this up because I think it's a good reminder for the fact that, I know something's not happening in here. Okay, so I want to be able to visualize my data, so I'm going to use ggplot for that, and I need to bring in my data, and this time it's not as a CSV file, it's as an Excel file, so I need the readxl package to be able to do that. So I don't need to install ggplot2 because I've done that in a previous lesson. I just need to pull it from the library. It's already installed, so Control Enter does that. Now notice line 5 is commented out. Now I don't have readxl in there, so I'm going to have to uncomment this. And now I want to run line 5, which is using the install.packages. So that function is going to grab the package and install it. And what am I installing is going to be the readxl package. So Control Enter on this. Notice in my console, it's downloading everything. Sometimes these packages are ready to go. Sometimes when you're downloading them, you have to be able to compile them afterwards. As I said, if you're using a Mac and your Mac has already limited sort of compilers on there based upon the version that you have, some come ready to actually do coding, some are not. If it's already comes set and ready to go, these will work perfectly fine. If you start running into trouble there, it typically means that a compiler or something that you need to run the code is not, or to install the code and execute the code afterwards, is not already on your system. For Macs, I'm not 100% sure, but our IT people are great for that. They've helped in previous years. They're still willing to help now. So we just need to reach out to the technical support in the math and stats department, school, whatever. And they'll help you make sure what you need on your Mac is set up. So please do not hesitate to do that, because the last thing that you want to do is leave this to the last second and no one's able to get in contact with you, or no one's able to contact you back. There we go. All right, so I don't need this anymore because I've already downloaded the package. And notice if I go to my bottom right screen here under packages, ggplot2 already has a check mark because I loaded that from the library already. And if I go down here, readxl is now in here, but it does not have a check mark. So I've downloaded it. It's in the library, but in order for me to use it, I need to pull it from the library. So let's pull it from the library by using line 6. So line 6, just using the library function, pulls readxl from there. And now notice in that bottom right screen, not this block over, but the next block over from there, readxl now has a check mark. So okay, all the packages that I need are now installed and pulled from the library, ready to use. Okay, so the first thing I need to do is I need to bring in this data. So what I want to do here, well, actually, let's stick with this for just a second, because I want to, hopefully I'm going to break something here. So what I want to do is I'm going to use the readxl function, read_xl. The data, the Excel data that I'm bringing in is called dummy var. So D and V capital, everything else is lowercase, .xlsx. Now if I click this, and this is what I wanted to show you here, notice that it can't find this file. So I'm given a warning, or given an error, not a warning, an error. So it cannot do this. It says path does not exist. So what I've said is, let's grab, using the readxl function, let's grab this file, dummyvar.xlsx. It can't find that. Why can't it find it? Well, I haven't told it where to look, or I have told it where to look and it's looking in the wrong spot. So remember, everything that we did previously was for lesson 2, and I stored lesson 2 in a specific folder. For each of my modules or each of my lessons, I tried to put them in their own folder. So right now it's looking in lesson 2's folder to try and find this dummy var xlsx file, and it's not there. So I have to retell it where to look. So again, I've stored all of my Excel files, or all of my data files, in the same spot I've stored my script files. So lesson 3 is in the exact same place as this dummy var.xlsx. So I need to change my working directory. And again, if I go up to session at the very top of my screen here, down to set working directory, I can choose, the last option is choose a directory if I have it stored in a different directory, but I am going to do to source file location. So right now what's open in terms of my source file is my lesson3.r. So I'm saying wherever lesson3.r is, use that folder as my reference folder to pull everything from, or my working directory. So by default, it uses the function set working directory c.users Gary downloads module 2. So okay, this is now where it's pointing. So if I go back here, and I want to store this all in the variable named dummy, if I go back here and execute this line, now it works. It's there now. It knew where to find it. So if you ever get this error, typically it's because you haven't set the correct working directory. So you just need to go back and you just need to double check that. So you can either use the setwd function. I wouldn't recommend this. Just use the session button up at the top, set working directory into source file location if you're keeping everything together. All right, so if we notice in the top right corner, this variable dummy has 15 observations or 15 rows. Now, the original data that we had only had 10. So let's take a quick look at this. And I can see all of my observations, or I can see my entire data frame by just calling the variable name. So we stored everything to the dummy variable. So if I just call dummy, it's going to print to the console all 15 observations. And remember, if I didn't want all 15, if I just wanted to see the first couple, I could use the head function or the tail function, which is going to give me the first 6 or the last 6 observations. But here I did not do that. It's going to print out the full data frame or the data set that I have. There is a limit to the number of things that it can print off, but since it's only 15, it's perfectly fine here. All right, so notice the first 10 rows for location, I have 5 that are street, 5 that are mall. Okay, so that makes sense based upon what I had beforehand. But now the last 5, 11 to 15, are downtown. Okay, that wasn't part of our original example here. We only wanted 2 levels. So this is going to be used when we add in another level to the data. So what I want to do right now is I want to get rid of, or I want to build a new data frame that is not going to have the last 5 rows. I don't want the ones with downtown in them. So how do I build this? Okay, so I can tell what rows I want and which rows I don't want. How do I do that? I'm going to store this new data frame in the variable toLevel. How do I get the levels or the rows that I want? Well, first I have to reference what data frame I'm pulling things from. So I'm referencing dummy. Now I want to pick specific rows and specific columns. So I use my square brackets for this. I'm doing this because these are my round brackets. Square brackets, there we go. I have my square brackets, which means I need to include a row and column. So we separate the rows and columns by the comma. So row comes first, columns come second. Now notice after my comma, I have nothing there. That means I want all of my columns. But I don't want all of my rows. So what I'm going to do is I'm going to put in a new variable, a true and false variable. So it's going to have 15 rows, and every time it's labeled true, I want to include those rows. Every time it's labeled false, I don't want to include those rows. Now, I could just say I want rows 1 through 10, but let's suppose they weren't in this nice order. It wasn't the first 5 being street, the next 5 being mall, the next 5 being downtown. Let's say they were all randomly put in there. I just want to grab the ones that are not downtown. So what I do is I am going to include this line here. So I'm saying, let's look at the column location inside of that dummy data frame. And I'm asking the question, is the entries in each one of those, so if I look at the column, I'm going to go through each entry in the column, is this equal to, or in this case, is this not equal to, so that's where the exclamation mark comes into, is it not equal to downtown? So every time it sees either street or mall, it's going to reference true. If it sees downtown, it's going to reference false. So if I just do this line here, notice I have a vector of size 15 that prints out where the first 10 observations are true because the first 10 rows do not reference downtown, but the last 5 are false. So if I put this vector, and that's exactly what I'm doing here, I'm putting, again, that dummy $ location not equals to downtown, I'm putting in that true and false vector, so it's only going to grab the rows that are labeled true. And if I print this out now, notice I have a new data frame called toLevel that only has 10 observations, the first 5 being street, the next 5 being mall. Perfect, everything that we want. All of the columns are still there because I didn't specify removing any. All are perfectly valid here. Okay, so the first question that was asked is, does the model, and we can see it right above here, does this model make sense? This y is equal to beta naught plus beta 1x plus beta 2d underscore m, or subscript m. So how this would make sense, first we want to do this visually. So let's use ggplot for this. Now remember, with ggplot, this builds on different layers. So the first layer is the data that I'm bringing in. So using the ggplot function, I'm saying my data is equal to 2 level. So I'm using that data frame 2 level. Now my aesthetics is, again, where this is my second level. This is where I'm mapping specific columns in my data frame to points, or not points, but objects inside of my kind of like my grid that I'm building for my my graph. There we go. So I'm saying the x-axis is going to represent households. So again, households is my numerical variable. I'm including that in there. My y is going to be my sales. Oops, my y is going to be my sales. There we go. I'm looking at the wrong ones. This is starting on line 18. So my y is going to be sales, and my geometry, which is my third layer of this, is how do I want my objects to look now. So my x and y, these are going to represent points, or they would be representing points on my graph. How do I want them to look? Well, I want them to look like points. I don't want them to be connected by lines or anything else along those lines, so I'm using the geom underscore point. Okay, so if I execute this, notice my graph pops up here. So looking at this graph, kind of by default, I don't quite see, and again, remember what we would expect to see if this is true. Again, you can see above here. Oops. There we go. I would have my graph, and I would be able to do 2 lines of best fit, where these 2 lines have the same slope, so they increase at the same rate or decrease at the same rate, depending positive slope increase, negative slope decrease, but they are separated by the intercept. Now, if I'm looking here in my graph in R, if I were to do a line of best fit, well, it definitely looks like it's increasing, but it doesn't look like I would have 2 different lines. But the problem here is all of my dots are black. There's no distinction between the 2 different layers. I don't know, based upon this on this graph, which ones represent mall, which one represents street. So let's break this apart. So using now line 20, I'm starting with the same first level. My aesthetics are almost exactly the same, but now I want to color each one of my points, and I'm coloring them based upon location. And again, my third layer, that the geometry of it, I want it to be points. So what should change in this graph once I execute this is the ones that are labeled as mall and the ones that are labeled as street should be 2 different colors. Okay. So now we can kind of see that my blue ones here, which represent my street, these are kind of starting down here, where my red ones here, which represent mall, do seem like they're a little higher up than what the street would be. So if I kind of did lines of best fit in here, and I can kind of quickly do this using ggplot, not actually modeling it, but using ggplot, let's see if I can do 2 different lines of best fit. So I'm doing all of the same 3 levels. So this is starting at line 24 of my code. But now in line 26, what I'm adding on here is this geom underscore smooth. So what this is going to do, the method I'm using is the linear model, and standard error is equal to false. I just want to do the lines of best fit in here. Now this SE equals to false. If I didn't include this, let's just get rid of this for a second. If I executed this, this is just going to get me lines of best fit, 2 different lines based upon my 2 different colors. But it's also giving me this gray sort of error. This, it's giving me my confidence interval, or my standard error in these calculations. I don't want this in here. I just want my lines of best fit. So let's put this back in here. There we go. So now looking at this graph, I have two different colored lines, one red, one bluish. They are separated, so the intercept is different. The slopes, they do kind of have the same slope. Again, what we're going to expect here, because we are only dealing with limited data, and this is a sample, we would expect that it's not going to be perfect. They're not perfectly going to have the same slope. There's going to be some difference in here. And the intercept, maybe it's a bigger jump, maybe it's not a bigger jump. This is what we get into when we run the hypothesis test. Right now, we're just kind of seeing, does the assumption of this model make sense? Should we even go through the hypothesis test? And in this case, I would say these lines have relatively the same slope. They do have a different intercept. Okay, that's enough for a hypothesis test. So let's do that. Okay. Now another thing to note. This is coming in part 2. Or sorry, part B of this. So it says interpret the practical meaning of beta 2. As I said, there is always a reference level. It's where we start. Where we start, again, if I go back here, let's actually switch up my screens. Let's have this here. Oops, that's not the one I want to do. This is what I want to do. Move over. When we pick that reference level, and again, I'm emphasizing this point. When we pick that reference level, this is what happens when we set the variables that are inside of our model equal to 0. So our reference level, that starting point, is going to be for beta naught. So in this case, this D, when this is equal to 1, is going to reference our next level, not our reference level. So we can reorder these things, and I'm going to show you in just a sec, based upon this graph, why we want to order things in a specific way. We don't need to. I just think it's easier for at least me to interpret. It might be easier for you to interpret which one we want to be that reference level. But the reference level is when the variables are equal to 0. Not all the variables, the dummy variables. And in this case, there's only the one dummy variable, but when there's multiple, it's going to be all the same thing. And we'll talk about that in a second when we see 3 levels. It's when they are equal to 0. That's our beta naught. The next level from that reference level is how does it change? It changes by whatever the beta is for that dummy variable. In this case, for D, it's beta 2. How are we changing it by? We're changing it by beta 2, and that's going to be the effect on the mean response compared to that reference level. Okay, let's jump back here. And let's switch up my screens. Now, actually, before I change up my screens, notice here D sub M. So I'm using this as mol. So when this is equal to 1, it's going to represent mol. When it's equal to 0, means it's shut off, it's going to represent that reference level. In this case, since we only have mol and street, street would be my reference level. That would be my starting point. Okay, so let's change up screens here. Now, why do I want street to be my reference level? Well, if I look at the intercepts, or if I look at my graphs here, which line is on the very bottom? The line that's on the very bottom would be street. So I want this to be my reference level. I don't need to do this, and we'll see in just a sec. I don't need to do this. But in this case, I want street to be my reference level. I want to say if I was going to order the different levels of my categorical variable, I want street to be the very first one. So when D is equal to 0, it would reference street. When D is equal to 1, it referenced mol. Okay, so there we go. So if I just expand the columns, as I just did in the global environment, And this is done for level 2. So our data frame with only the 2 levels in there. Now notice we have 4 columns: location, sales, store. Store is not really important because store is just telling us this is observation 1, observation 2, observation 3. That doesn't matter. And households. Now we know households and sales, these are numerical variables. Location, though, that's a categorical variable. And right now it's sitting as a character vector where it has 10 observations, it has 5 streets, 5 malls. So I need to make sure that R knows that this is in fact a categorical variable. So I want to be able to change this. So how did we do that before? We used the factor function. But I'm adding in a slight twist to this now. Because if I were to run, I'm going to uncomment out line 30. If I were to run line 30, it would say, let's look at 2 level, location. So we're looking at the data frame 2 level. We're looking at the column location. I'm going to re-reference that column by taking that column, so 2 level, location, and putting it through the factor function. So if I do this, I run this line. There we go, it's changed now. So location is now a factor variable or a categorical variable with 2 levels, the levels being mall and street. It orders them by default alphabetically. So mall comes first, street comes second. But what I said is I want, because if I'm looking at my graph here, I want street to come first, mall to come second. Okay. Why is this important to us? It's not overly. But let's build the model first, and then let's re-examine this and why I changed things up here. So I'm going to skip. I'll go back to this stuff in a second. So now I want to build the model. So I'm going to call this level2.lm. This is my linear model. I'm assigning to this variable. I'm going to build my linear model using the lm function. So the lm function, my first 2 inputs are simply going to be, what is the formula that we are dealing with? So the formula is, whoops, I just touched the mic, so that probably made a weird sound for you folks. Sorry about that. Do not touch the mic. Bad mic. I'm trying to explain sales. So sales are explained by the households and location. So again, if I'm looking at my model, the 2 variables of interest in there are my x1, and in this case my d, which is going to represent my categorical variable. So the numerical variable, my x1 is households, and locations is my categorical variable. So households plus location. And then I'm telling what data to use it from, so the data is coming from level 2. Okay, so if I build this, and let's run a summary on this. The main part here is the coefficients. We'll talk about some other things afterwards when we talk about the validity and how we choose certain models, and that's going to come by what we have on the bottom here. But right now, let's just look at the coefficients. So the first column represents which ones I'm dealing with. My second column is my estimate. So these are my B's, not my betas. These are my B's, how I'm estimating. So I have the intercept, so this is going to be my B sub naught. This is going to be my estimate for beta naught. So my estimate here is 46.57. Now households, this is for my beta 1. So my estimate, this is for B1. My B1 is 0.85105. So that's my estimate for beta 1. This is going to be my slope. So it's positive, so it means I'm increasing, and we see that it is increasing. It's not increasing overly quickly because it's less than 1, but it's still increasing nonetheless. Oops. And then my location is street. Now this is negative. So this is my beta 2. Sorry, this is my B2, my estimate for beta 2. So this is negative 29.21575. Okay, so what does all of this mean? When I'm talking about my very first level, and again, how this was ordered, by default, oops, you can see up in the global environment, again, this was done alphabetically. So right now it thinks my very first level is mall, my second level is going to be street. So when D is equal to 0, and I can actually, let's write this down here. I should be able to see this right above. So when D is equal to 0, our model is y is equal to 46.57557 plus 0.85105 x1. And again, I don't care about the location because I'm talking about when D is equal to 0. So this is the formula we have. This represents the formula when my line is red, because again, this is for my mall. Now, sorry, for my mall. Now when I go to street, which we can see street is my second level, so this is when D is equal to 1. So when D is equal to 1, what do I get? I have y is equal to 46.57557. Now notice here in the graph, to get from mall to street, I have to go down. So that is why I'm negative here. I'm negative 29 and change. So this is now minus 29.21575 plus 0.85105 x1. So this part stays the same. How it changes as x increases stays the same, but the starting point, so in this case we're talking about sales, so sales are going to decrease, and this is by thousands, so it's going to drop by 29 and change thousand. So when we go from a mall location to a street location, we're actually getting less sales based upon this data that we have. And how much less? On average, we're starting at 29,000 less sales in that given month. Okay. Why did it matter in terms of which one I wanted to start with first? Well, when there's a lot of these, I don't really like to kind of, some are positive, some are negative. If I pick the one always at the bottom, then I'm always increasing. So my other estimates that are referencing my different levels are going to be positive here because I didn't pick them. I let R do it. R did it alphabetically. So it put mall first, which just happened to be the line at the top. Street came second, which was my line at the bottom. In order to get from mall to street, I had to drop. So my intercept is going to be negative. Okay. As long as you're taking that into account, it doesn't really matter about ordering them. Personal preference, I like doing it, but it's not the end of the world. So how do we change the order of this? So this is at line 29. So I'm going to go back and I'm going to uncomment out line 30. At line 29, what we're doing here is exactly the same thing. So I'm taking my data frame 2 levels. I'm replacing the column location with it now being a factor variable, but I'm adding in this second option, or the second input into the factor function, where I'm going to now control which levels come first, or the order of the levels. So I'm going to create a vector. This is where my C, it's going to combine things together. It's going to create a vector. I'm going to assign to that vector the name levels. So this is the input that it needs to take. So there is an input variable name inside of the factor function called levels. It receives a vector and it tells us, or I'm telling it exactly how I want to order the levels of this. And I'm saying I want street to come first and mall to come second. So if I run line 29, notice in my global environment here, my location, factor with 2 levels. Now street comes first, mall comes second. Again, if I output, notice changing it to a factor variable. Again, nothing changes. I can go with the structure here. So if I use the str, the structure function, it's just going to print out exactly the same as kind of what I already have up here in the global environment. So if I'm just doing this from a console, I can see exactly the same thing. Or if I'm just inside of our studio, I can just click on my 2 levels and it's going to show me exactly the same thing here. Now, if I rebuild my model, I'm not changing anything here. And again, print out the summary. Notice there is going to be a change. what changed here in my model? My estimate for beta naught, that intercept, is now different. So before, it was 46.57557. Now it's 17.35982. Well, because I'm starting at street. That is my starting point. Households, notice that my slope has not changed, as it shouldn't. My location mall, 29.21575. So that hasn't changed, except for the fact that it's now positive. So it's saying that if I start on street, if I sell nothing, or if there's no household, so if, again, assuming that x1 is equal to 0, it's not going to be equal to 0. There's always households around, but assuming x is equal to 0, the sales would be estimated by the intercept, which would be 17,000 and change. If we change to a mall location, so again, D is equal to 0 represents street, D is equal to 1, which is why I have a D sub M inside of our model, up, which we see up top, D sub M representing our second level, so it's when that's equal to 1. When that's equal to 1, we see an increase of average sales by 29,000 and change. So that's the difference of going from this line to this line here. When we're at street, our starting point is the 17,000 and change. When I jump up to mall, I'm now 17,000 plus an additional 29,000 and change. So it's the sum of the two things which is going to get me here. But really, when we're talking about it, we're talking about the difference. The difference is 29,000 and change, or 29.21575 thousand and change. Okay, so we've interpreted the practical meaning of this. Now what we want to do is we want to run a hypothesis test. How are we doing for time? Well, we're getting there close to this. So let's get through this part here. Because I said I really want to only make these an hour. Now these are going a little bit slower because, again, I'm really focusing on the R code as well. As we get a little bit more comfortable with the R, I'm going to be going through these a little bit faster. But for now, let's just take our time with this to make sure we're understanding how the R code works. All right, so what I want to do is I want to do a hypothesis test. It would be really nice if I was able to... Ooh, actually, I think I can do this. Let's learn as we go here. Okay, so I'm on this screen here. What do I want to do? Do I have... Nope, that's not what I wanted. Nope, close that up. There we go. It was closed captioning me for a second. That's not at all what I wanted. What do I want here? I want... here we go. White screen. Perfect. All right, so what are we doing? We're doing a hypothesis test. So our null hypothesis is we're saying beta 2 is equal to 0 versus the alternative, beta 2 not equal to 0. So again, we saw in the picture that my two lines, my red line and my blue line, my street location, my mall location, it does look like they have a different intercept. So what we're saying here is, for H naught, we're saying this is from the random sample that we took. There is no statistical evidence to indicate that it is in fact different. It just so happened to be that we picked 5 stores from mall, 5 stores from street, and it looks like there is a difference between the two, but there isn't. Versus the alternative here, again at alpha being 0.05, so we want a 95% confidence, or we're setting our type 1 error to being only 5%. Again, type 1 error is when we reject the null hypothesis, but the null hypothesis is in fact true. So when we make that mistake in the looking at the extreme ends of our tail and saying, oh, wait a second, we're in this area, so this can't possibly happen, or can possibly happen, but the likelihood of this happening is so incredibly small that I'm rejecting the null hypothesis and accepting the alternative. But the null hypothesis is actually true. Okay. So in this case, we're saying that there is actually a significant difference between these two things. Okay, so that's the first step. Now what we need to do is we need to either look at the t-value or the p-value. So looking at r, and you can see that from my screen above here, the t-value for beta 2, or t sub beta 2, this is equal to 5.223. Now we can go through and we can find the critical value of all of this. Or again, I can look at the p-value. So my p-value is equal to 0.00122. So option 1 so we can find the critical value. And if, again, we're dealing with the t-value, so this is almost like a normal distribution, but again, we're using the t distribution from this one, so it's slightly skewed. So if our t beta 1 is greater than CV, and usually we get the extreme ends of the tail because this is a two-tailed test, because I'm saying I don't care what beta 2 is going to be. It could be positive, it could be negative, it doesn't matter. So if it's positive, I'm saying if the critical value of the positive part of this is, if my t-value is greater than that, or if we're talking about the negative side of this, or t beta 2 is less than the critical value, when we're talking about the other ends of the tail, when the negative side of this, only we really kind of refer to this one again. This is all stuff you would have done in the 2601. So not if it's less than the positive one, but less than the negative one. So right tail, this is left tail. Really, we're focusing on the right tail of this. So if it's in that critical range where we reject, then reject H naught, accept HA. The alternative, option 2, look at the p-values. So if p-value is less than alpha, reject H naught, accept HA. There we go. So the two different options. So I'm not going to bother finding the critical value because it automatically gives us in the R output the p-value. So notice in this case the p-value is equal to 0.00122, which is less than 0.05, which is alpha. Thus, accept the alternative. So at alpha being 0.05, there is a diff between the two locations. All right, so that's the hypothesis test. Now I want to find the confidence interval. So we want to find where does, because again, what we've done here is we found the estimate. So the estimate for beta 2 is 29.21575. Where does the true value of that lie? Where does beta 2 actually exist? So now we need to do a confidence interval. So let's jump back over here. Can I switch this screen? On white screen. There we go. Going back. That was kind of convenient. That'll probably come up handy later on. But I don't think that saves. But it's okay. This is being recorded, so you can go back and look at it later afterwards. So let's build the confidence interval. Where does that beta 2 actually lie? Because we've rejected the null hypothesis, we've accepted the alternative. Now remember, if we fail to reject the null hypothesis, then this part doesn't matter because we don't have enough evidence to say that there is a difference. But we've rejected the null hypothesis. We say at alpha being 0.05, it is statistically significant that there is a difference between these two. Where does the true value lie? So we're going to use the function confint. I'm going to put in my linear model, and I'm going to say the level I want for this. I want a 95% confidence interval. By default, it's always going to do a 95% confidence interval, but, oops, let's... I hate these things. I just had a screen pop up saying, oh, updates need to go for Windows. Restart computer. I'm like, I'm in the middle of recording. Absolutely not. Do not restart right now. That's my rage for today. Sorry. Actually, I would be kind of upset if this did restart because I'm an hour in and then I'd have to record that whole hour over again. Yeah. Okay, so using the confint function, there we go. I said by default it has a 95% confidence interval. If we're doing something we only want a 90% or we want a 99, we just need to adjust this parameter here. I can leave this parameter out and it's automatically going to go to a 95%. But I think in some of the examples that, or the exercises I've done in the assignments, I've put something that's not 95%, so you're going to need this in here. So hint, hint, you'll need this part. So notice this does it for all of my estimates. I don't need it for all of them. I just need it. Let's actually change this screen up here. There we go. R is now right over here instead of up there, much larger. Perfect. See, this is the fun part about doing it when I'm just talking to a camera and not talking to actually you folks in the classroom, because someone would have said, hey, wait a second, you're on the wrong screen. Change up the screen. Fix this now. We're just not there. Just not there. Okay. So again, notice we have estimates, or we have a confidence intervals for all of them. We only want the last one here for the mall location. This is for our beta 2. So again, B2, the estimate for that, is 29.21575. So we need to go a little bit to the left. We need to go a little bit to the right on that one to find where the true population parameter is. And how far to the left, how far to the right? Well, we're going to the left to 15.9881022. So that's our lower bound. Our upper bound is 42.443391. So what does this mean for us? It means the true difference between going from a street location, which is our first line, to a mall location, so that jump up in sales, that increase in sales, what is that increase actually going to be? Well, the true population parameter for this, or the true value of this, is either going to be around approximately 16,000 to 42,000. So that's going to be the difference. So even though the estimate was at 29,000, the true population parameter being 95% confidence, it's either we're going to see an increase of about $16,000 in sales all the way up to about $42 and change thousand in sales. So that's what the confidence interval is telling us. Again, we get confidence intervals for the other ones. I only care at this point in time in terms of our beta 2 because that's the only thing that I was testing in the hypothesis test. Okay. So that's everything at this point in time, up to 2 levels. We'll continue this on with 3 levels and build from there. Really, the extension of this is going to be very, very straightforward. But let's take a little bit of a break and come back in the next lecture. So we'll see you back then, and we're going to be talking about, again, 3 levels instead of 2 levels. Yay! Until then.